Hello and welcome to this lecture. In this video, I'll be walking you through the concept of exponential time complexity and demonstrating how it works in practice using the Fibonacci series. To get started, let's look at the Fibonacci series. The Fibonacci series is a sequence of numbers where each number is the sum of the two preceding ones, starting from 0 and 1. For example, this simple illustration demonstrates how each new number in the sequence is created by adding the two numbers before it. This highlights the recursive nature of the sequence and setting the stage for exploring its complexity. In most definitions, the Fibonacci sequence starts with the 0th term as 0. When we start counting from 0, the 4th term in the Fibonacci sequence is indeed the 5th element. So the 5th element is the term at index 4, which is 3. Let's dive into understanding time complexity of big O of 2 to the power of n. In this piece of code, we're calculating the Fibonacci of 4. To understand how Fibonacci function works in the code, you'll see a tree representation on the right side of the screen. Each node in the tree represents a function call, and each split shows the two recursive calls it makes. In this code, fib of n, which represents the Fibonacci of n, is a recursive function. At the beginning, a base case is defined to prevent the function from running indefinitely. It simply returns n if the numbers of the Fibonacci sequence are 0 or 1. But if n is greater than 1, the function calls itself twice. Once with Fibonacci of n minus 1, and again with Fibonacci of n minus 2. And this recursive call will continue until the base case is reached. Now, let's imagine calling Fibonacci of 4. This will be displayed as a recursive tree on the right. At the root of this tree, we have Fibonacci of 4, which splits into two branches calling Fibonacci of 3 and Fibonacci of 2. Each of these branches further splits into more recursive calls. To calculate Fibonacci of 4, we first need to calculate Fibonacci of 3, then Fibonacci of 2, and so on. Therefore, Fibonacci of 3 is the sum of Fibonacci of 2 and Fibonacci of 1. For Fibonacci of 3, we need Fibonacci of 2. To calculate Fibonacci of 2, we need Fibonacci of 1 and Fibonacci of 0. Finally, Fibonacci of 1 and Fibonacci of 0 will return 1 and 0. As we can see, the base case is reached, and now we can calculate the Fibonacci values for all the previous steps. Fibonacci of 2 is equal to 1. As it is observed, we then calculate Fibonacci of 3, which is the sum of the Fibonacci of 2 and Fibonacci of 1. Finally, to calculate Fibonacci of 4, we must also compute the second function. To calculate the right side function, which is Fibonacci of 2, the function will go through the computation of Fibonacci of 2 and its base cases. Therefore, it will compute Fibonacci of 1 and Fibonacci of 0. After calculating it, Fibonacci of 4 will return 3. As we can see, Fibonacci of 4 has been computed. Now let's dive into the intuition behind the time complexity of this algorithm. At each level in the tree, the number of nodes approximately doubles. So at level k, there are about 2 to the power of k nodes, which represent the function calls. This doubling leads to an exponential time complexity that is big O of 2 to the power of n for the recursive Fibonacci function. To summarize, when calculating Fibonacci of 4, the operations will stop at level 3, regardless of the number of function calls at that level. Therefore, the number of nodes in the tree representing the function calls is approximately 2 to the power of n minus 1 for Fibonacci of n. However, in big O notation, we focus on growth rates and ignore constants and small differences. Therefore, we simplify 2 to the power of n minus 1 to 2 to the power of n. And finally, note that as n increases, the number of operations grows extremely fast and can quickly become unmanageable for larger values of n. This rapid growth is characteristic of exponential time complexity. For example, when n is small, the time taken is manageable. But as n rises to 5, 10, and beyond, the growth in operations becomes dramatic. I hope you learned something valuable and enjoyed this lesson. Thank you for watching the video, and please feel free to share your thoughts.